So in this video, we'll be integrating ln of 1 plus 3 sine squared of x over sine squared of x from 0 to pi over 2 using Feynman's trick. If you don't know the trick, you can read about it online and then come back to watch the video. With that said, let's begin. So we'll start by defining j of alpha. We will introduce a parameter alpha to replace the 3 in the original integral. And so this is what we have. And then we will differentiate this with respect to alpha. So we have j prime of alpha. And here we will use Leibniz integral rule to rewrite the differentiation inside of the integration operator using a partial derivative. So this will look like this. And then notice that the sine squared of x on the denominator is independent of alpha, and so this can be easily factored out of the derivative as follows. So now we are just simply evaluating the derivative of the natural log, which we can do using the chain rule. So here we have times sine squared of x, which is the derivative of the inside with respect to alpha, and then the derivative of the outside is the natural log, which we have 1 over here. And so this can be simplified to equal sine square, 1 over 1 plus alpha sine squared of x dx. And now we will divide both sides of the fraction by sine squared of x over sine squared of x, which is the same thing as dividing by 1, so we're not changing the quantity as a whole. So this will give us cosecant squared of x over cosecant squared of x plus alpha dx. And now we will rewrite the denominator using the trigonometric identity. Cosecant squared is equal to cotangent squared plus 1. So this will give us 0 to pi over 2 of cosecant squared of x over cotangent squared of x plus 1 plus alpha dx. And here we can introduce a u substitution to simplify the integral. So we will let u is equal to cotangent of x and du is equal to minus cosecant squared of x dx. And the limits of integration change from infinity to 0 instead. So we have infinity to 0 of minus 1 over u squared plus 1 plus alpha du. The minus flips the integration limits, and so this leaves us with 1 over root 1 plus alpha arctan of u over root 1 plus alpha from 0 to infinity. And arctan of u approaches infinity as u approaches infinity. So this is simply equivalent to pi over 2 root 1 plus alpha. Now that we have the j prime of alpha, we'll try to find j of alpha by integrating the above expression with respect to alpha. So we have pi over 2 root 1 plus alpha d alpha. And the pi over 2, of course, can be factored out. So we have 1 over, this can be rewritten as 1 plus alpha to the minus 1/2 power. And now this is just a simple application of the reverse power rule. So we have pi over 2 times 2 alpha plus 1 over 2. And this is an indefinite integral, so we need the plus c constant at the end. And so when we simplify this, we will simply have pi alpha plus 1 to the 1/2 plus c. So next we need to find the value of c, the constant of integration. To do this, we will look at j of alpha is equal to 0, which is the same thing as the original integral, 0 to pi over 2 ln of 1 plus, but here we have 0 sine squared of x over sine squared of x dx. And notice that 0 sine squared of x is simply equal to 0. And so we have ln of 1, which is also equal to 0. So this is simply just equal to 0. Therefore, we know that if alpha is equal to 0, the integral itself is equal to 0. So we can let 0 is equal to pi root 0 plus 1, and then we have plus c. So if we solve this, we get c is equal to minus pi. Finally, we can evaluate the original integral by finding j of alpha is equal to 3. And so when we substitute this, we get pi root 3 plus 1. And now we know c to be minus pi, so this is minus pi. And this is 2 pi minus pi is equal to pi. And there we go. So thank you for watching today's video. If you learned anything, please consider subscribing, and we'll see you next time.